we're going to illustrate calculation of a standard deviation and talk a little bit about the meaning. Okay, so we have some values, 3, 5, 6, and 6, and these are the values of which we want to calculate the standard deviation. We're going to call these x values. And we note there are 4 of them, so n is going to stand for how many x values we have. There are n equals 4 x values. Now the first thing we want to calculate is the mean of the x values. That's a very straightforward calculation. It's just the usual average. We add these numbers up and divide by 4. So 3 and 5 is 8, and 2 6s, that's 12. That gives you 20. So the sum of the x's is 20. The mean is sum of the x values divided by n. Chalk is kind of sticking. Let me fix that. Okay, the sum of the x values divided by n. I'm writing that kind of small, but you should be able to read that. That's 20 over 4 equals 5. So that's our mean. Now, I've got a column here. I don't really need to have a whole column to fill in with the mean, but we use the Greek letter mu or x bar, x with a bar over it. Either of these is a standard notation for the mean of our x values. So our x values all have mean 5. Well, our x value mean is 5. Okay, and I'm just writing down the 5s here because we're going to use the mean value along with the x value to calculate the deviation of the x value from the mean. Okay, the deviation of the x value from the mean is just the x value minus the mean and the absolute value of that. So 3 deviates from 5 by 2. We don't worry about the fact that 3 is less than 5. If we wanted to calculate what's called a residual, that would be negative 2. But in this case, just because 3 is less than 5, we're not going to make that negative. This is always going to be positive. Okay, a deviation is always non-negative. Okay, and x value is 5. Well, the mean is 5. It's always 5. So this deviation there is 0. The deviation of 6 from the mean is 1. The deviation of 6 here from the mean is 1. Now, just to clarify this column here, I'm just going to write the 5 once so that it doesn't look like we have a 5. We have this 5 being repeated 4 times. There's just one 5, that's the mean. And the x value, we take the difference between the x value and the mean, absolute value of that difference, and that's our deviation. Now the deviation shows us how far each of our x values is from the mean. So if we average these deviations, it's going to give us one measure of the spread of the deviation. Okay, if the x values deviate a lot from the mean, we're going to get a big average deviation. Otherwise, we're going to get a smaller deviation. So what do we get? We get 2, 1, and 1. That adds up to 4. Sum of the deviations is 4. And the mean deviation is 1. I'm not going to write out the entire calculation of that, but we're just taking the mean of these 4 numbers. There are 4 of them. We add them up, we divide by 4, we get a mean deviation of 1. That is a reasonable indication of how much these numbers are spread out. On the average, they're 1 unit from the mean. That's not the standard deviation. Okay, standard deviation, well, it's a little crowded here. I thought I'd given myself enough room, but I hadn't. These videos are one-shot deals. We're going to have to live with that. So sigma is what we use to stand for the standard deviation, and the standard deviation is the square root of the, quote, average, and there's an asterisk on that, the square root of the, quote, average of the squared deviations. Okay? Now, we've already got the deviations, so what do you think we mean by the square root of the average of the squared deviations? You should be able to deconstruct that phrase and calculate this quantity, except that you probably would make one mistake, but I recommend that you stop and actually try to interpret that before you see me do it. Okay, well, square root of the average of the squared deviations. We've got deviations, okay? We need squared deviations. Well, the squared deviations are here 4, 0, 1, and 1, okay? And then we want to average those. So to average them, well, the sum of the squared deviations is 6. Okay? Now, if we want the average of the squared deviations, if we didn't have that quote and that little note, we would divide this by the 4 numbers that we've got here. Okay? Now, for reasons that you can't understand unless you had a calculus-based development of normal distributions, so you don't want to go there, but you just accept this. There's a rule that says if n is less than 30, then when you calculate the average, you don't divide by n. Remember, n stands for how many x values there are. You divide by n minus 1. So instead of dividing by n, which would be 4, we divide by n minus 1. 4 minus 1 is 3. We're going to divide by 3. So the average squared deviation is 6 over 3, which is 2. And then the standard deviation, remember we use sigma to stand for the standard deviation, is the square root of that. Square root of the, quote, average of the squared deviations, which in this case is square root of 2, which is approximately 1.4. Now this differs somewhat from your mean deviation, not too drastically, but it differs somewhat. If you had a larger number of values, this would actually probably come out somewhat closer to your mean deviation or average deviation. But that's the meaning of the squared deviation, and it's a measure of how much your numbers are spread out from the mean. Okay, so I just wrote that statement down. Again, the standard deviation is a measure of how much the x values spread out from the mean. Now, another picture of this distribution. Here we have balance. Okay, we got a fulcrum here at 5, and we got 3, 4, 6, and 7 here. Okay, so those might be distances along the balance, the beam, or whatever. If we put our 3 here at 3, center it on 3, put a 5 here, and we put a weight. If we put a weight on 3, centered at 3, another weight centered at 5, and 2 weights centered at 6, then they're going to balance here. That's going to be well balanced. You could take a ruler, a light ruler, and put weights on them at 3, 4, 5, 6, and 7 inches and see how they pretty much balance. Of course, if you're not centered in the center of the ruler, the balance won't be perfect, but that's okay. You get the idea. Okay, now, and there's a picture that goes with this, and the picture is just this. If you had a larger number, let's say you had 100 numbers here that had a mean of 5 and a standard deviation of 1.4. Then on certain pretty broad conditions, under certain pretty broad conditions related to probabilities in a way that we don't want to really talk about right now, those objects would, or those outcomes would tend to line themselves up in a way that can be approximated by a curve. Okay, so here's your x bar or mu, your mean. In this case, that would be like 5. Okay, then you can construct what's called a normal curve, and I'm going to show you very quickly how to construct that. Okay, well, to construct it, I'm just going to draw a line down the middle here. Okay, then I'm going to come over here at some distance, a distance corresponding, say, to the distance from 5 to 6. And actually, no, I don't want to use that distance. I want to use the standard deviation. I'm going to come over a standard deviation here. And I'm going to construct a line 60% as high as that line. Now, I'm just doing this, estimating it, but and here I'm going to construct a line that's 1/7 as high. And on the other side, well, the same thing, and of course that line isn't particularly vertical, but you get the idea. Okay, and I'm not trying to make this perfect. Wouldn't be able to if I tried. And then I construct a bell-shaped curve through these points. And that curve really should have peaked here. I just can't bring myself to turn the chalk quickly enough. That line should have been a little higher, should have been a little over this way to make it straight. Okay, but this is a basic rough picture of a normal curve. So this is your mean, or x bar. This is x bar plus a standard deviation. And this is x bar plus 2 standard deviations. And here you're at x bar minus a standard deviation, and here you're at x bar minus 2 standard deviations. And that's a picture of the normal curve. 34% of the curve, 34% of the area of the curve lies here, 14% lies here, about 2% lies out here, and the same percentages occur as you move to the left of the mean. And that's the meaning of a normal curve. Now, if you have a normally distributed set of numbers, and again, if you're observing things out in the real world, often, very often, you will have a normally distributed set of numbers, then if you stack up hundreds of objects, you're going on a balance like this, it's going to tend to follow something very much like a normal curve. I can't go into any more detail on it than that, but that's kind of the meaning of the normal curve. Now, I've given alternative labelings to these points. The mean is at what we call z equals 0. Z is a standard letter used to describe how many standard deviations we are to the right or left of the mean. So if we're 1 standard deviation above the mean, then z is 1. If we're 2 standard deviations above the mean, z is 2. It's 2 standard deviations below the mean, z is -2, etc. The corresponding x values for the distribution that we just calculated, where we have a mean of 5 and a standard deviation of 1.4, well, the mean is 5, standard deviation is 1.4, so if we move 1 standard deviation to the left, we're 3.6. 1 standard deviation to the left of that is 2.2. Go to the right, we get 6.4, 7.8. One additional comment at the end related to confidence intervals. At z equals 1.96, 2.5% of the area under the curve lies to the right of z equals 1.96. Maybe a little hard to read what I wrote there, but it's much like what I wrote here. At z equals -1.96, 2.5% of the area under the curve lies to the left. This is very relevant if you're trying to find, say, a 95% confidence interval. If you have some x variable that's distributed like this, then the chances are, if you randomly pick an x, you have a 95% probability that that x will be between here and here. Only a 2.5% probability that it's to the right, and a 2.5% probability that it's to the left.